So support vector machine, it's another abbreviation is SVM. The short form is SVM. So it can be used for classification tasks. So classification means what is the classification task? So if you have multiple data items with multiple labels and you want to distinguish all the data points with different labels, you want to classify them, then that type of task is called your classification task. So SVM can be used for regression problems and classification problems as well. I have also given some examples in the last chapters what is a regression is about. But mostly your support vector machine is widely used in the classification objective. So what is the support vector machine actually? Let's see the second slide. So the actual what happens, the objective of SVM algorithm, there is an algorithm in the SVM that we need to follow. So the objective of SVM algorithm is to find a hyperplane in an n-dimensional space. And here n means what? N means number of features. So if you are given with a data set, then there must be a number of features, and you within that n-dimensional space or n-dimensional features, you can distinctly classify all the data points. Okay. So classification is mostly vital for predicting the categorical class levels. So if there are different class levels of different categories, so let's take an example of web personal homepage or web page classification. So let's say there are multiple homepage classifications. Take it in the form of multiple features. Suppose they are x1, x2, x3. So you are just abbreviating as xi. And let's say the home page, the web pages are actually basically of two types or two label types, and those two label types are shown like this: yi equals to +1 or -1. So here x1 may correspond to the home page, or x2 may correspond to the welcome. So while classification, if you have number of labels and using those labels you need to classify multiple data points, then in that case this type of SVM is really helpful. And always this label types like yi equals to +1 -1. So if you have two types of labels, let's say this picture here, so you have two types of data, either cross or circular shape. These are two types or two label types. One of them is +1, one of them is -1. If you want to classify them, then mathematically we can represent it like this. And looking at the data set cross or the cross data or the circular data, in order to find a hyperplane in between them to distinguish them or classify them, it should be derived in the format of a function. So this is the function actually. F is your x corresponds to your y. So x is actually the number of feature, and y is the label that you want to classify the data points. So in the here linear classification is linear if you have a linear distribution of data. So mostly in place of binary classification problems, such as you have only two labels present in your data set. So for that data, it is really helpful, this type of data set. Suppose you have animals data set and fruits data set. If you want to classify them, then it will be coming under the binary classification problem. So this is one simple example of the SVM. So, okay, let's go to the discriminative classifier. So it actually talks about the advantages and criticism. So what does it mean? SVM, support vector machine, is actually used for classification. So what type of data it will classify and how it will classify? So it is mostly related to that. So advantages is what? So whenever you have a set of data set of features, and you want to do some sort of classification, whatever accuracy you expect, that is generally high. The prediction is really good in terms of accuracy. And if you have your examples or training samples. What does it mean by the training examples? That means whenever you have a data set, some portion of the data set you consider as a training data set, and some portion of the comes into your testing data set. So first, what model, the SVM model, machine learning model that you will train, you will train it using the training examples, and once the model is trained, you will apply the testing data set, the remaining data set part, to the model again and see the prediction, how it is behaving, whether it is behaving correctly or not. Okay. I'm planning to show you some sort of practical example. There will be like the way I have shown you the clustering, if you remember, using the Python, the Jupyter notebook. So similar type of implementation I will show you in SVM, so that it will be more clear to you what we are discussing about. But after um, winding up this chapter, I'll show you one day, maybe probably in the on ground class or in the online class on Thursday. We will talk about that. So whenever your training example actually have errors, it also works really well in that kind of situation. And fast evaluation of the learned target function. So whenever you train your data to your SVM model, so after that, when you apply that model to the testing data, so while evaluating or learning the target function, it also gives us a good accuracy in that. But that when disadvantage uh, it's it takes a lot of time. It's the time complexity is really high. It takes a long amount of time for training the data. So when you want to train the model, let's say your model doesn't have anything, first you need to feed some data into the SVM model, so that the model will be fit particularly. But for fitting that or training that model, it takes a long amount of time. And there are certain weights associated to the SVM models, and it is really difficult to, sometimes it also gets difficult to understand those weight associated functionality in the SVM model. And it is not always that much easy to incorporate the domain knowledge. So first, in order to apply the SVM to your given data set, you need to have a proper domain knowledge. So sometimes there are two types of scenarios actually. We will talk about that: linear SVM and non-linear SVM. Whenever the data format is linear, it is pretty straightforward to train the model. But in place of your nonlinear model, there is a different trick, which is called kernel trick, that you need to learn about. And that applying the kernel trick is again much complex in its it is in its own kind again. And SVM. So actually, this slide gives you overall goal about the SVM. What is actually SVM? The objective of your support vector machine algorithm is to find as I told you, is to find a hyperplane which will separate the different data labels present in your data set. And it that hyperplane can be drawn in an n-dimensional space where n corresponds to number of features, and it will distinctly classify the number of data points present in the data set. So to separate the two classes of the data points, there are many possible hyperplanes that could be chosen. How, I will show you in the next slide. And here the main objective or ambition is to find a separating plane to separate the data attributes that has the maximum margin. Again, that is another one important thing. What is maximum margin? So maximum margin is actually the maximum distance between data points of both classes. Actually, maximizing the margin distance will provide some sort of reinforcement so that future data points can be classified with more confidence. It looks a bit complex now. Let's look into that later in some other slides. Just to give you some history about the SVM. So SVM is actually recently developed by Hapnik and his team in the AT&T Bell Laboratories, and they have created this technique which is called as support vector machine. So it is actually mostly used for the classification and numerical prediction or the regression problems. So some of the applications most often used, the application most famous examples of SVM are the handwritten digit recognition. So what is this? There is a data set for digit recognition. There are different digits 0 up to 9. So using those digits, you can construct your different digits of numbers. So different people can write the digits in different way. Okay, your way of writing the digit 5 is different to the way I write the number or the digit 5, right? So there is a data set called MNIST data set. You can also search it online. So it is a huge data set, and SVM, if you see, there is an application. There should be a lot of Python implementation, machine learning implementation of support vector machine on the MNIST, which is the handwritten digit recognition. And it is really famous. If you would like to take a look at it, you can just search online, look for SVM MNIST dataset. It will give you the implementation of your support vector machine, and you will see how effectively it classifies the digits through the SVM model, the support vector machine. And like that, we use it for object recognition or speaker identification or some sort of time series data analysis tasks. So these are some of the mostly hugely used applications of the SVM. Let's see the practical application of it. What does it mean by the support vector machine? So as you see, this is a data set, and here our main goal is to find a linear hyperplane, that is the decision boundary that will separate the data. What does it mean? So support vector machine is highly preferred by many as it produces significant accuracy with less computational power. And support vector machine is abbreviated as SVM, and it can be used for both regression and classification tasks. And the main objective is to find a hyperplane in the n-dimensional space where the n dimension can correspond to n number of feature, which can classify the data points. So here we have square data points and circular data points. So what are the possible ways then? Let's see what are the possible way of having the hyperplane. So this is one possible solution. If we see another solution, so this is another way, another possible solution. So there are different ways of partitioning the data sets. Okay, so here see other possible, these are multiple possible solutions in which you can partition your data set. So that circular objects or attributes will be classified as one label, and your square attributes will be classified as another one label. So in between all these possible solution, okay, let's see this next slide. You have B1 and you have B2 here. Both of them partition our dataset effectively. But which one is better, whether B1 or B2 is better? That is what SVM is about. So let's see different scenarios of it to understand more better the SVM, that is support vector machine. So here, what do we need? We actually need the margin width. The more the margin width, the better is the selection of the hyperplane. Hyperplane is actually the plane which partitions both of the different attribute types or the different data set of different labels. So to separate two classes of data points, there are many possible hyperplanes. Okay, and that could be chosen. So our objective is to find a plane that has the maximum margin, that is the maximum distance between the data points for both the classes, that is circle class and the square class. So maximizing the margin, that is this one, distance, provides some reinforcement that so that the future data points, whatever any new data points that will come in the future to be added to the data set, okay, those future data points can be classified with more accuracy or more confidence. That's what our aim is behind implementing the support vector machine. So you have this plane here, hyperplane B2, hyperplane B1. So B2 again has two different margins, margin hyperplane, that is B21. Here B, small b21, small b22, small b11, small b12. These are called margin hyperplanes. Just remember. And the middle one is the main hyperplane, partitioning the two different data labels or data attributes. So here, if you see the distance in between two margin hyperplanes, here in case of B1 is more in comparison to the marginal hyperplane distance to B2. So which one we will choose? We will choose the more distance, marginal distance, which is B1. So you need to take the distance between two attributes of two class levels wherever the marginal hyperplane distance is more, so that it will classify the data attributes more effectively. Hope you got the idea. What are we trying to achieve here? We need the hyperplane which has more width, that is more marginal distance, hyperplane distance. Okay, the general philosophy. Just a simple example. So here, these are two different labels or different attributes, and here it has a small margin, whereas this picture it has a large margin. So we need to always find an hyperplane or choose a, there may be multiple scenarios of hyperplanes. Which one to choose? You need to find the hyperplane who will maximize the margin. So here the right case has more larger margin than in comparison to the small margin. So we will go with the right side here. Let's see some mathematical analysis, which is more important here, and these are also related to the one problem or one example I will be showing you. You don't have to go into the depth of mathematical derivations. It's really easy. It's not that difficult. You can just remember. So if you have seen in past that in your mathematics related, so the equation of a line, that is y equals to mx plus b, right? So let me write it out. It's something actually related to that. So if you write y equals to the equation of a line, it is actually related to this mx plus c, if you remember. So this is the equation of line, and here x is a data point, c is a constant, and m actually belongs to your slope. Okay, so our formula is somewhat related to this, the mathematical formula, the equation of line, that is y equals to mx plus v. So the generic equation of separating the hyperplane, it can be written as like this: wx plus b equals to 0. Okay, this is your generic equation. So here x represents the attributes, and the wb represent the parameters of the hyperplane. This is the main equation of the hyperplane, and to which side of the hyperplane our points will be aligning, again the equation changes accordingly. So if a data instance xi, suppose xi can belong to either side of the hyperplane, so it depends on the sign of wx plus b equals to 0, whether it is positive sign or negative sign. So as in this figure, it shows one side of the hyperplane is 0 and the other side of the hyperplane is your 1. Okay, sorry. One side is your -1 and other side is your +1. So for the purpose of binary classification, we can always find a hyperplane that places instances of both the classes in the data set, that we said data set is actually sorry, we can find a hyperplane that places instances of both classes on the opposite sides of the hyperplane. So thus resulting in the separation of the two classes, that is square class and circular class. So if there exists a hyperplane, then it can perfectly separate the classes in the data set. And we can say the data set is linearly separable. So for this, this is your main hyperplane, the bold red one, and the dotted red ones are your marginal hyperplanes. And the distance between two marginal hyperplanes is your margin, distance of the margin. And that margin can be signified with this formula, 2 divided by the norm vector of W. Okay. And if you say this hyperplane, the equation of this hyperplane will be -1, and all the attributes will be labeled as negative side or the -1 side of the classification. And the top, this portion, the circular data set portion, it will be signified as Wx plus P equals to +1 at the positive sample. So looking at this analysis, we can say that support vector machine relies on a basic function. Okay, the function of X, that X is a data set, the collection of data attributes inside the data set. So positive and negative levels, this is a binary classification problem. Either we have positive samples or we have negative sample. Anyone, either if this one is -1, this portion, then it is negative sample. If this is +1, this is classified as positive samples. So for +1, your formula will be like this: Wx plus B should be greater than or equals to 1. For negative, it should be less than or equals to -1. This is the one thing, most important thing you need to remember. Okay. And the classification in SVM is actually related to this basic function. Okay, so the linear model, as I was talking about, linear SVM is a classifier that searches for a separating hyperplane with a larger margin, and that is why it is called maximum margin classifier, and this is the basic formula. So when do we say that the data is linearly separable then? Okay, so here whatever we are talking now, it is actually the linear SVM. The nonlinear SVM is a different complex kind. We will look into that later. So there may be infinite or multiple lines or hyperplanes separating binary classes or two classes having data points, but we want to find the best one. So which is the best one? The one that will minimize the classification error and maximize the marginal hyperplane distance. Okay, whichever hyperplane will be able to minimize the classification error on the unseen data, that is our best model or best hyperplane. And SVM always searches for a hyperplane with our largest margin. Okay, and that is the maximum marginal hyperplane. The short form is MMH. And yeah, I want to tell you one thing. The W, as I told you, the X represents the input vector. Whenever some data is given to you, it will be in the format of vector. We will look into that in one example. So W is actually is the normal direction of the plane. So here you will just take a perpendicular. It's related to the slope of a line, right? Similar to slope of a line. You will just take it like this. So there is a vector W who is perpendicular to the normal direction of the plane. Okay, for this it may be like this. So it should be, there should be a 90-degree angle. Okay, and it should be perpendicular. This is what W is. And B is some sort of a constant or a threshold that you will choose. So for a given data point W, if W dot X is evaluated to be bigger than B, then it belongs to a class. And if it is evaluated to be less than b, then it belongs to another one class. This is again some in-depth derivation of it, which you shouldn't be more concerned about. Just for now, remember this is the main function for linear SVM. Okay. So as we were talking about in the linear SVM, our main objective is to maximize the margin, and that maximizing the margin is shown by this formula here. If you need more clarification about these derivations, you can refer the book. And as we know, the generic equation of the hyperplane that I was saying you, the dot product of Wx plus b equals to 0. So here x represents the attributes and Wb represent the parameters of the hyperplane. And yeah, so that's the formula for positive and for negative instance. This is how we change the formula, whether Wx plus b greater than equals to 1. We again formulate it, whether it is less than equals to minus n. And while if you need to minimize the margin, that is again some sort of optimization problem, which is related to Lagrange multiplier method. The more derivation, in-depth derivation is in the book. If you want to refer, you can refer that. But for now, you just should be concerned about the margin formula and this major function for the hyperplane. Okay, so here learning the linear SVM, a support vector machine actually takes these data points and outputs the hyperplane, which in 2 dimensions. It's simply a line, okay, and that line can best separates the tags. This line is the decision boundary, and anything that falls to the one side of it will classified as one label, and anything that falls to the other side will be classified as the as a different label. So this one, the Wx plus b greater than equals to 1, it will point to your positive samples, whereas anything less than equals to minus 1, it will point to your negative samples or a different label inside the data set. So see one small analysis. So a separating hyperplane can be referring to the equation of a line W into X, W dot product X, because these two are the matrices, so there should be a dot product plus B equals to 0. So where we are considering the W as the multiple weight vectors W1, W2 up to Wn, and B is considered as a bias or a constant. It's a scalar value, it's a constant value. And these are some of the parameters which are required for training the support vector machine model. So if there is a two-dimensional space, so for that we can write the formula in this way. W0 plus W1, it's two-dimensional, right? So each dimension, that is x1, then this is x2. Each dimension will be associated with the weight. So this is the formula. So using this, if you want to find out the hyperplanes defining the sides of the margin for this, then it will be in this way, referring to which this formula. That is this W0 plus W1 x1 plus W2 x2, if it is greater than equal to 1, this is the positive size of the hyperplane, the marginal hyperplane, and the less than equals to minus 1, which signifies to the negative side of the hyperplane. So this is how you will get the hyperplanes. Then comes support vector. What does it mean by the support vectors? So any training data sets or tuples means it is considering as one row. So as each point is a two-dimensional point, so it is considering a row, means that is x1 and x2. That is one point. And it will fall, if any training tuple will fall in the hyperplane h1, h2, that is the sides defining the margin, these are the support vectors. So what does it mean? So see, suppose there are data sets. So here these are some of some of the points. Here we have some circular points. This is our hyperplane. Oh, sorry. Okay, so main hyperplane, and these two sides are our marginal hyperplane. This is the marginal distance. So if there are some points which will come here, which will be in the border here, so they actually play a major role in defining the hyperplane or marginal hyperplane, and these are called as the support vectors. They are meant for support of the hyperplane. That is why they are called the support vectors. Let's see one example here. So see this example carefully. You will be given an assignment related to it. And if you have any questions, you can stop me and ask me while during the explanation. So see, suppose you have a set of data points. So these are the data points x1, x2. These are different two-dimensional data points x1, x2. And we want to use the support vector machine algorithm or model to train a classifier, and they will classify these data points. How they will classify? Either some points are in the positive side or they are in the negative side. And here we are defining the support vectors of all these points also. So how? Through this column AI. If some of the points has the AI value as 1, that means they are support vector. So for example, the point 1, 2 has support vector as 1. So that is a one means it is a support vector. But here see 5, 9, 0. So AI is 0 means this is not a support vector point. It doesn't lie on the border of the hyperplane. Hope you understood it, right? So this is given, and Y actually gives you the label, whether it is a positive or a negative label. And in looking into this, you will first do an analysis. Then from there, after you get a conclusion, you will find out these two testing data, 2,5 or 7,2. Okay, which side of the hyperplane they will lie, that you need to decide. Let's look into what we are trying to do. First, we will find out a decision boundary. Okay, then after finding the decision boundary, you will classify the testing data, that is this, which side they will lie. Okay, these are the things that we are going to do. So this is our data set. Here see, first P12 y is, this is a support vector. That means that the plane will go through this. The hyperplane, marginal hyperplane will go through this 1, 2. Okay. And because AI 1 here, that is the support vector. And here this is a positive sample, y positive sample. Then your 2, 1 is -1. So, and again it is a support vector. So there should be another one marginal hyperplane signifying or pointing to the negative label or negative class type will go through this point here. Then suppose your point 0, 1, which is again a support vector. Okay, and the y is 1 here. So here somewhere through this your line will go. Let me draw it like this. So this is how it will go, and there should be another one. This is how it should go. So for 0, 1, you see it is 1, so it is positive side. Okay, for 1, 2 it is 1, so again it is positive side, and 2, 1 it is negative side. So whichever points are here, they should be negative, and whatever are here, they should be positive. Let's look at here for 3, 9. You can see that it is not a support vector because it is 0, as it is not going through the plane. And Where is that? 3, 9. And the y value is 1 means it is lying in the positive side. Let's take 6, 2. This one, 6, 2. So 6, 2 is not a support vector because it is 0. That is why no line is going through it. And the y is -1. That means it is a negative sample. So here it is in the negative side. Hope it's clear what I am trying to explain you. Now let's see our derivation. So this is a binary classification problem. There are two points, that is x1, x2. So we should have two weights as w1, w2. We will take first 1, 2 point of the positive side and 0, 1. Okay, of the positive, and then 2, 1 which is the negative. Okay, we will take all the support vectors, 3 of them defining the hyperplane, to find out the value of w1, w2 and b, which will be necessary for our decision boundary derivation. So for all these points, for P12, you will write the formula like this. That is your Wx plus B equals to something, right? So that something will again signify to whether it is a positive or a negative side. Correct? Whether it will be in a positive or in the negative side. So what we will write for 1, 2, W1 into 1 plus W2 into 2 plus B. B what we don't know. Okay. And 1, 2 is on which side? Positive side. So here it should be equals to 1 based on this formula. Okay. Wx plus b greater than equals to 1 for positive sample, less than equals to -1 for negative sample. Hope it's clear. So like this, in the same way for 0, 1, you will write w1 into 0, w2 into 1 plus p equals to 1. For p2 to 1, you will define the same formula. And here 2, 1, as you know, 2, 1 coming in the negative side. So that is why it is -1. So when you will solve this quadratic equation, you will get the values of w1, w2, b as in this way. Okay. And now if you, this is the main formula, that is this one, okay. So in the main formula, if you just put all the values what you have here, so the formula, final formula will be like this: -x1 plus x2 equals to 0. This is our main decision boundary here. We now form the decision boundary. Now let's see how it looks. The way I was drawing it, the picture is in the same way. So this is your decision boundary now. Positive side, negative side, y plus 1, y minus 1. Okay. Now next thing, what do you need? We need these 2 points, 2, 5, 7, 2, where they will lie, whether positive side or negative side. That's what we need to find out. Oh, let's see here. So first for 2, 5. Okay. First for 2, 5, we will see what we will do. We will take this formula, the decision boundary. Okay. And we will just apply the points. In 2, just apply x1, and in x2, just apply 5. And you got 3. 3 which is greater than equals to 1. That means it is classified as a positive sample. Here y equals to 1. And 7, 2, it is giving negative. That means it is classified as a negative sample. And just plotting them in a figure, see how it looks. The 2, 5, yeah, 2, 5 is in the positive side, and the 7, 2 is in the negative side. Okay. So this is a sample problem. You will be given a similar problem in the assignment as well. So next, so let's just stop here, take a look at the problem and go through it. And in the next class, we will start from here. Okay, we won't be able to finish everything now. and there is a lot of concepts to take in, so just review the slides, and we will start from the this one, not linearly separable, that is non-linear support vector machines. We will start next Tuesday.